Alright, so we're going to be going over lesson 3 for chapter 10, which is going to be over physical changes. We have one vocab word, so that's physical change. Physical change is a change in size, shape, or form or state of matter in which the matter's identity stays the same. So this would be if we were chewing food, the carbon in the apple still stays carbon. Changing in shape and size. Matter may change physically, but does not change the type of matter that it is. So this is saying we're going to stay gold or we're going to stay carbon. Things along that line. Change in shape and size. Chewing food breaks down the size of the matter, but does not change the type of matter. So there's a difference between changing the type of matter and changing the size of the matter. A change to the states of movement of the molecules have to change their speed, to change the states, the movement of the molecules have to change their speed. So, if we're going from gas to liquid, we're going to be going slower. The molecules in whatever, we'll say water because that's an easy example, will have to start moving slower. And we're going to start talking about how heat plays a role in that too. Adding thermal energy. So thermal energy is another name for heat. Heat and energy, you have to remember, are two words for about the same thing. Heat is a type of energy. So when you're adding thermal energy, it is added to matter, when thermal energy is added to matter, it becomes more excited. When we talk about excited, we say it has more energy, and that makes it move faster. In solids, when molecules move fast enough to overcome the bonds, so there's bonds between the molecules, all of the molecules in a solid, and when they get excited enough or they have enough energy or heat applied to them, they actually can break those bonds, and then they reach the melting point. The melting point is the temperature where the solid becomes a liquid. So those bonds break, and then we have a liquid. When liquid molecules gain thermal energy, they have enough energy to break bonds and reach their boiling point, which is evaporation. When that happens, they evaporate and become gas. So, when we say we break bonds in solids, there's still bonds there. There's still bonds that are holding the things together because the liquids we know are still condensed enough or held together enough, and they still have bonds. It's just not as strong, and there's not as many bonds. Removing thermal energy. Removing thermal energy, when gas molecules lose thermal energy, they slow down, bond closer together. That makes liquid. This is called condensation. When liquids lose thermal energy, they slow down even more, and the bonds hold them together even closer, and that's solids. So we talked about just a second ago was how we needed to add energy to go from solid to liquid to gas. Here we're talking about the reverse process. We're going to be removing energy, so removing heat. So this would be if we start as a gas, we could say that we put a hot glass into the freezer. Right away it's going to start, the water vapor is going to start condensing on the glass. So it's going to go from water vapor to liquid, and that's condensation, and then from there it's going to go from liquid to ice, and that would be the freezing. And we think about it in the freezer because that's the way we take away the thermal energy, or we decrease the temperature. This is called a phase change graph. You have to kind of look through this, click to add text. I'm not sure what happened there. But here you see on our y-axis we have temperature, right? 100 degrees Celsius, 0 degrees Celsius, negative 20 degrees Celsius. And going across the bottom right, we should have just the state that it's in. So here you can see it says steam. We would also call that water vapor. At 100 degrees Celsius, which is the boiling point for water, you have water and steam. So water starts to turn to steam. It's important to note that water can never be over 100 degrees Celsius. At any point, if water starts to be over 100 degrees Celsius, it's no longer liquid water, and it's become water vapor. As we start to go down, so here's this flat line means that we've hit our boiling point. You can be hot steam. I mean, you can be steam that's 300 degrees Celsius, but you're never going to be water that's 300 degrees Celsius. So here, our area between 100 and then this to 0 degrees Celsius, that's water. Water can exist in any temperature in that range. After we hit that point, 0, that's our freezing point, so that's going to be ice and water. And the same thing with steam, or with water vapor. You're not going to be ice, or you're not going to be water at anything below 0 degrees Celsius. So make sure you know how to read this. If you have questions, make sure you ask during class. Here's another one. I added this one because as good as the water vapor and water and ice example is, it's important that you know that this applies to every single thing, not just water. So gold has a melting point. So we normally think of solid gold, which would be starting down here. If you add enough thermal energy or heat to it, you would get to the gold's melting point. If you're going in this direction, if you're going across to the right, you would get to its melting point. After you started melting it, or after it melted, you'd have the liquid gold. And then if you added enough energy, like a lot of energy, you could get the gold to go into the air as vapor. So you'd have gas gold essentially, and that would be vaporization or evaporation. If we're coming back down, it's something we would normally think of as carbon would be one we normally think of as a gas. Let's say oxygen we think of as a gas. So if you take away a bunch of energy from oxygen, you're going to have that condensation. So you're going to have liquid gas right here, or excuse me, liquid oxygen right here. And that's something we don't really normally think about. If you take away enough, you'll get to the freezing point, and then you would have solid oxygen. Notice how melting and freezing are lined up at the same point. They're the same temperature. They're just depending on which way you're going. If you're going from solid to liquid, you're melting. If you're going from liquid to solid, you're freezing. Dissolving. The example here is salt and water. Salt's properties and water's properties do not change. Salt is still salty, right? We keep using the ocean as an example. If you've ever been in the ocean, you know how salty the water is. Salt breaks down into smaller molecules so that you can't see them, and the salt is mixed evenly through the water. So you have the salt and the water. We call it salt water, but those two things are still separated. And we'll see a picture of that in just a second. Make sure you know that this is a physical change. This is not a chemical change, which is what we're going to be talking about in the next lesson. So here our blown up warped picture. NaCl over here is salt, sodium chloride, maybe you've heard it called that. And our little HOH, that's H2O, which is water, right? So what they're saying here is if we add water to our NaCl, if we add water to our salt, the water gets in between these molecules on this side, and it actually separates them. So we still have the same stuff, it's just not in the same form anymore, right? It's been broken down, which we talked about as a physical change. Conservation of mass. Molecules are the same before and after physical change. So, let's finish this slide first. Total mass is the same before and after physical change. There is the same number of each molecule present. The molecules might just have changed state or shape. We're actually going to be doing a short experiment over this. If you have a closed system, which means nothing can move out of the system. So we have a beaker with a lid on top of it. No matter what you do, so if you boil the water, even though it looks like there's less water, that water is now water vapor, and all of the water is still accounted for. So when you measure it, or when you weigh it, the mass is still going to be the same. And because of that, we can assume that we're still going to have the same number of molecules, because we know that the mass can't change if the molecules stay the same. So here is kind of an example. We have a test tube that has a few different liquids in it, and I'm not too, I don't want you to get hung up on sodium hydroxide or copper sulfate. But what they're showing you is on this side we have 67.25 grams in here when we when we mix our sodium hydroxide, when we mix our two substances, doesn't matter what the reaction is down here, we still have the same amount of weight. We still have the same amount of molecules in our beaker. That does it for this lesson.